This is the next video in the chapter on chemical bonding and molecular geometry. We have finally learned about all the different types of ions, both single atom and multi-atom ions, and now we're going to put them together into ionic compounds. So an ionic compound contains both positively charged cations and negatively charged anions. And we're going to use red for cations and blue for anions. And so if you wanted to predict how many cations and how many anions were in a particular ionic compound, you might guess that they would have the same number of cations and anions, but it's not actually the case. What is the same number is the charge. We are trying to get the charge to cancel out of all the positives and all the negatives, so we have a neutral compound. So the charges must cancel out, so the compound is neutral. So we can use what we know about predicting the charge of a particular ion, or knowing, in the case of a polyatomic ion, we can predict what the formula of an ionic compound would be given any two ions, preferably a cation and an anion. So let's take a cation, magnesium 2+, and an example anion, nitrogen 3-. And we'll try and predict what that compound might look like. And there's a fairly simple rule for making that prediction. You simply take the charge for each of the atoms and you place it as the subscript for the opposite ion. So we'll write that out. The cation charge becomes anion subscript and the anion charge becomes the cation subscript. And if it just so happens that it's necessary, because you have fairly large numbers as your charges and thus large numbers as your subscripts, you can simplify the ratio. So we can complete an example with magnesium and nitrogen. So we'll write them both here in a chemical formula. We'll take the 2 from the magnesium charge and place it next to nitrogen, the 3 from the nitrogen charge and place it next to the magnesium. And we don't need to simplify. 3:2 is an appropriately small ratio. So it's fairly straightforward as long as you remember what the charges are for each of the ions. And the same process works when you're using polyatomic ions as well. So let's think of a polyatomic cation. There's not many to choose from. We'll pick NH4+ ammonium, and we can pair polyatomic ions with monatomic ions, or we can pair polyatomics with other polyatomics. Both of those are possible. Let's make it extra complicated by picking a polyatomic anion. We'll do sulfate. So the same rules apply. We just take the charges and we swap them for the 2. The difference here is we need to be careful when we put in a subscript because there are already subscripts in the formula for the polyatomics because they have multiple atoms in them. So what we do is we just put parentheses around each of the polyatomics so that we can tell which subscript belongs to the polyatomic that indicates the number of atoms and which subscript indicates the number of ions. So this 4 indicates there are 4 hydrogens, and this 2 indicates there are 2 ammonium units. So the 2 from the sulfate goes under the ammonium, the 1 from the ammonium goes under the sulfate, but if it's a 1, we technically don't need to write it. It's usually left out. So we'll just leave it out. And then here, this subscript 2 for 2 cations, that goes outside of the parentheses. And you don't technically need to include the parentheses if there's only one of that ion, but I like to include them because it reminds me that that is a polyatomic and then it needs to travel together. Now, for a note, we have been talking about these compounds and we need to include their charges, first of all. So to prove to you that the charges are equal, we can do a little bit of quick math. So if we have 3 magnesiums and they each have a charge of 2 plus, and then we add 2 nitrogens and they each have a charge of 3 minus, that is going to be +6 plus -6. It's going to give us 0, which it should. And the same is true for this one. We have 2 of those NH4 plus units, which have a charge of +1. Plus we have 1 sulfate unit, which has a charge of 2 minus. And +2 plus 2 minus is 0. So if you created your ionic compound correctly, it should have a total charge of 0. Now for the note. We have been writing these ionic formulas, Mg3N2 and NH42SO4, as if they were molecules, but I'm sorry to tell you that it is simply not true. The formula for an ionic compound is not a molecule. It is simply a formula unit or a formula. It tells us about the ratio and nothing more. Let me illustrate to you what they do look like if they don't look like molecules. We're going to use red to represent sodium, and we'll use blue to represent chlorine, and our favorite table salt, sodium chloride. So if you wrote the formula, you would write NaCl, because sodium has a charge of 1 and chlorine has a charge of 1, and you might predict that you would be able to find a wild sodium chloride molecule that looked like this out in nature. And I'm here to tell you that that is not true. Instead, what it looks like is called a 3-dimensional lattice, or a regular repeating structure that alternates cations and anions. So it looks a little bit like this. If you have an anion, every anion is surrounded by cations. And then every cation is surrounded by anions, and on and on and on, to make a very large 3-dimensional compound. And we can draw in sort of the different ionic bonds between the atoms here. And you can picture them going out even farther past the edge of the drawing. So rather than finding a single sodium and a single chloride that are bonded together, it's more like lots and lots of sodiums and lots of chlorines all bound together into a lattice, and the ratio of them is 1 sodium to 1 chlorine. If you were to zoom in on a particular atom in this structure, for the sodium chloride rock salt structure, each atom is actually bound to 6 of the other type of atom. So each anion is bound to 6 cations, and each cation is surrounded by 6 anions, and those come together to form a large lattice. So you don't need to understand everything about how this sort of a lattice works right now. The most important thing you need to remember is, number 1, there is no such thing as a molecule of sodium chloride, and number 2, the formula is simply a ratio. It's called a ratio or a formula unit, not a molecule. This is by far the strangest type of way to start to talk about bonding, is to talk about three-dimensional lattices of ions. But they do so because of those charges that hold them together. And we'll talk about that in the next video.